So, in this lecture, let me continue with the previous lecture where I was doing the analysis of planar mirror waveguide. So, what I was doing was to find out the modes of a planar mirror waveguide, and what I did that I took the planar mirror waveguide which has refractive index n and metal deposited at x is equal to 0 and x is equal to d, and the modes of this waveguide I found out as Ey is equal to a sin m pi x over d, and corresponding beta are given by beta m square is equal to k naught square n square minus m pi over d square. So, what I got that I got this kind of variation of electric field Ey with respect to x, or this, and these fields propagate in the waveguide and sustain their shape as they propagate. They also propagate with certain propagation constants beta 1, beta 2, beta 3 and so on. Let me understand what they are. So, the field is am sin kappa m x, where kappa m is equal to m pi over d. If I write the complete solution, this is only Ey m of x part of the solution. Remember that there is t and z parts also. So, if I write down the complete solution, there it is sum am sin kappa m x e to the power I omega t minus beta m z. Let me write this sin kappa m x in the form of e to the power plus minus I kappa m x. So, if I do that, I get this, and then let me put it in this form. So, what I have got from here, I have got it e to the power I omega t minus beta m z minus kappa m x, and then e to the power I omega t minus beta m z plus kappa m x. What they are? And remember, you see now outside I have a constant, it is not a function of x. The x dependence I have included in the exponential now. The x dependence which was earlier here I have included in the exponential, and when I see this now, this is nothing but a plane wave because outside is a constant. So, and this is a plane wave which is moving in this direction, moving in xz plane, making certain angle from z axis, and this is a plane wave which is moving in plus z minus x direction. Okay. So, what I have got that this mode is nothing but the superposition of two plane waves, this plane wave and this plane wave with some phases. Okay. So, it is a superposition of two plane waves, one propagating in this direction, another propagating in this direction. If you look at the waveguide, this is x, this is z. So, this is xz plane, this is x, this is z. So, one wave is moving like this, another wave is moving like this, and this is what you have, that if you launch a wave like this, then it will get reflected, then reflected from here, reflected from here. So, all the time you will have two waves, one going in this direction and another going in this direction. Let me put them together here in xz plane. So, one is moving an angle theta m with z axis and another one is moving minus theta m angle with z axis, and this has to be the propagation constant in the medium of a plane wave. These are now plane waves. Plane waves will have propagation constant k naught n. So, this is the component of propagation constant in x direction. This is the component of propagation constant in z direction. So, if I now do kappa m square plus beta m square square root, then it comes out to be k naught n, and it comes out to be k naught n, because you remember that kappa m square is equal to k naught square n square minus beta m square, which means that this is indeed k naught n. This is indeed k naught n. So, the propagation constant in z direction is k naught n cos theta m. Let us understand it. If I take the components in x direction, I have one wave going in positive x, another wave going in negative x, which means that in x direction I have two counter propagating waves, and when I have two counter propagating waves, they give you a standing wave solution. They give you standing wave. So, in x direction I have a standing wave. In z direction, if I see, this also gives me propagation in positive z, this also gives me propagation in positive z. So, I have a standing wave in x which propagates in z. The energy does not flow out in x direction, the wave stands in x direction, but that standing wave pattern flows in z direction. This is the mode. So, these modes are nothing but the standing wave patterns. These modes are nothing but the standing wave patterns, and they are made out of two waves, one going in this direction, another going in this direction. I can now find out what is the effective refractive index of a given mode or effective index of the mode by beta m over k naught, which is nothing but k n cos theta m. So, for every mode I have different beta m, and therefore, the angles that the constituent plane waves make with z axis would be different, and these angles can be found out from here. For example, for n is equal to 1.5, d is equal to 1 micrometer, and lambda naught is equal to 0.633 micrometer helium neon wavelength, I find out that there are these modes, 4 modes. Let me look at them closely. The first one has effective index 1.4662, and the angles of constituent plane waves with z axis are plus minus 12.18 degrees. So, there are two plane waves, one making plus 12 degrees, another making minus 12 degree with z axis, and this is the standing wave pattern in x direction corresponding to those waves. The second one is with n effective is equal to 1.3599 with angles plus minus approximately 25 degrees. Yet another one is this with angles plus minus 39 degrees, and this one plus minus 57.56 degrees. So these are the modes. How many modes are there for a given waveguide? Well, let me look at this picture again, okay, and from here I know that kappa md is equal to m pi. So this m would be kappa md over pi, and kappa m is nothing but k naught n sin theta m, and the maximum value of this would be k naught n, because the maximum value of sin theta is 1. So the maximum value of km is k naught n, and this will give me what is the maximum value of m. So I put maximum value of km here, which is k naught n. So m max would be k naught n by pi, and k naught is equal to 2 pi over lambda naught. So this would be 2 nd over lambda naught. So the maximum number of modes that can propagate in a planar mirror waveguide would be a number, an integer, which is closest to but less than this, which is closest to but less than this. For example, if I have n is equal to 1.5, d is equal to 1 micrometer, and lambda is equal to 0.633 micrometer, there should be micrometer here, then 2 nd over lambda naught comes out to be 4.739, and this gives me the maximum number of modes as 4. So there would be 4 modes supported. So this is the analysis of planar mirror waveguide, which gives me insight into the modes of a waveguide, which is a structure which is quite intuitive, and light guidance in that structure is also quite intuitive. But this structure, planar mirror waveguide, is of very little practical use. For one, it is not feasible to make this waveguide that you have 1 micrometer film of certain material and you deposit metal on top and bottom of that and use it. Second, since it involves metal coatings, and metal is highly absorbing material, so as these modes propagate, they will attenuate very quickly. So they have very high loss. So this kind of waveguide is of little practical use, although it gives a good understanding of mode propagation. Okay, so now what we are going to do is to look at more practical waveguide, which is a symmetric step index planar waveguide, dielectric waveguide, planar dielectric waveguide, which is obtained by sandwiching a high index slab between two lower refractive index slabs. So I have N1, N2, N2 here, and N1 is greater than N2. Again, if you look, there is refractive index discontinuity only in x direction. Y direction, it is infinitely extended. In z direction also there is no index discontinuity and it is infinitely extended. If you look at the refractive index profile of this waveguide, then it looks like this. And let me put my x is equal to 0 axis in the middle of the waveguide, so that I can make use of the symmetry of the problem. Let it have a width d. The width d So, this is x is equal to d by 2, this is x is equal to minus d by 2. I can write down the refractive index variation with respect to x in this fashion. So, this region is mod x less than d by 2, while these two regions can be represented by mod x greater than d by 2. So, in mod x less than d by 2 I have refractive index n1, in mod x greater than d by 2 I have refractive index n2. And now my problem is to find out Ey and corresponding beta for this given n of x. So, how do I do this? Again go back to the wave equation corresponding to TE modes. Let me first solve the problem for TE modes. So, this is the wave equation for TE modes and this is the nx. So, how do I solve it? Well, I find that in this region and in this region and in this region, in all the three regions, the refractive index is constant. Although when I go from here to here and here to here, I encounter index discontinuity, but on this side and on that side the refractive index remains constant. So, I make use of this and write down the wave equation in this region and in this region, that is in this region and in these two regions. So, for mod x less than d by 2, I write it down as d2 Ey over dx square plus k naught square n1 square, because nx is equal to n1 in this region, minus beta square times Ey is equal to 0. And I also keep in mind that my effective refractive index, which is given by beta over k naught, effective refractive index n effective, which is given by beta over k naught, this should lie between n2 and n1 for guided modes. For guided modes, n effective would lie between n2 and n1, which means that beta would lie between k naught n2 and k naught n1. So, beta would be greater than k naught n2, while it would be smaller than k naught n1. So, when I write this equation now in these two regions, which are represented by mod x greater than d by 2, I write it as d2 Ey over dx square minus beta square minus k naught square n2 square times Ey, because nx is equal to n2 here. And why I have written it in this fashion? So that this is positive here and this is also positive here, because I am solving it, going to solve it for this condition, which is the condition for guided modes, for which the energy would be confined into this region. So, I represent this as kappa square and I represent this as gamma square, and these kappa square and gamma square are positive for guided modes, as I have explained. So, let me write these equations down again here. So, for mod x less than d by 2, I have got an equation d2 Ey over dx square plus kappa square Ey is equal to 0, and for mod x greater than d by 2, it is d2 Ey over dx square minus gamma square Ey is equal to 0, where kappa square is this and gamma square is this. What are the solutions? I know the solutions of these differential equations very well. This equation gives me oscillatory solutions, e to the power I kappa x or e to the power minus I kappa x or sin kappa x cosine kappa x, while this equation gives me exponentially amplifying and decaying solutions. So, if I write the solutions in the regions mod x less than d by 2 and mod x greater than d by 2, I find that in this region it is oscillatory solution a cosine kappa x plus b sine kappa x, and in the region mod x greater than d by 2 I have exponential and decaying solutions, but out of these two solutions I retain only exponentially decaying solution. While exponentially decaying solution and not exponentially amplifying solution, because I want a solution which gives me guided modes, and for guided modes the energy should be confined into the high index region and it should decay down as you go away from the high index region. As you go towards infinity, x is equal to plus minus infinity, the energy should decay down. So, I cannot take exponentially amplifying solutions. That is why for x greater than d by 2 I have chosen the form of solution c e to the power minus gamma x, and for x less than minus d by 2 I have chosen the form d e to the power gamma x. These a, b, c, d are some constants which can be determined by the boundary conditions. What are the boundaries? Boundaries are x is equal to plus d by 2 and x is equal to minus d by 2. But here I can make some more simplification. What simplification I can make is to utilize the symmetry of the problem. How can I utilize the symmetry of the problem? Let us see. I have the wave equation for TE modes like this, and this is the n of x. I see that this is symmetric about x is equal to 0, which means that n square of minus x is equal to n square of x. Now, in this equation, if you replace x by minus x, then you get d2 ey of minus x divided by d of minus x square, that is x square, plus k naught square n square of minus x minus beta square ey of minus x is equal to 0, and this is nothing but n square of x because of the symmetry of the profile, which means that I now have two possibilities, which are ey of minus x is equal to ey of x. If I put ey of minus x is equal to ey of x, I get back the same equation, or if I put ey of minus x is equal to minus ey of x, then also I get back the same equation. So, there are now two possibilities, one is this, another is this, and they are known as symmetric modes because this is the property of a symmetric function and this is the property of an anti-symmetric function. So, these modes are known as symmetric modes and these modes are known as anti-symmetric modes. The simplification it introduces is that out of those two functions cosine and sine, I can pick one here and one here. Since cosine is the symmetric function and sine is the anti-symmetric function, so symmetric modes would now be represented by E y of x is equal to a cosine kappa x for mod x less than d by 2 and c e to the power minus gamma mod x for mod x greater than d by 2. For anti-symmetric modes, I will have E y of x is equal to b sine kappa x for x less than for mod x less than d by 2, and then I have d e to the power minus gamma mod x for mod x less than d by 2, but I shall have to take care of sign when I go from left side or right side. What do I mean to say is this: if this is x and this is d by 2, this is minus d by 2, this is x is equal to 0. Now, if you plot a sine function in the region mod x less than d by 2, so it goes something like this, and now in the n2 region for positive x values, you will for x greater than d by 2 you will approach from here and then it decays down, while for x less than minus d by 2 you will approach from here from negative side. So, here you start from positive side and decay down, here you start from negative side and then decay down. Okay. So, to take care of that sign I will have to put x over mod x here. So, these are the symmetric modes, and remember that I am doing the analysis of TE modes. TE modes have non-vanishing components of E and H as EY, HX and HZ. What is left now? I need to find out the relationship between A and C. I need to find out how these solutions are connected at the boundaries. For that I will use boundary conditions, and I have learned that the boundary conditions are when you encounter an interface between two dielectric media, the boundary conditions are tangential components of E and H should be continuous. Tangential components of E and H should be continuous. What are the tangential components to the boundaries? This is the waveguide, this is x is equal to plus d by 2, this is x is equal to minus d by 2, this is y, this is z. So, to this interface which is x is equal to plus d by 2 or x is equal to minus d by 2 here, the tangential components are y and z, x is the normal component, and here the non-vanishing components are EY, HX and HZ. So, the tangential components are EY and HZ. So, these EY and HZ should be continuous, and if you look back to the three equations which relate these three components of E and H, then I find that HZ is nothing but some constant times dEy over dx. So, Ey and dEy over dx should be continuous at x is equal to plus minus d by 2. So, let me apply these boundary conditions. Let me do it for x is equal to plus d by 2, the same would be obtained for x is equal to minus d by 2. So, I put Ey should be continuous at x is equal to plus d by 2, which means a cosine kappa d by 2 should be equal to c e to the power minus gamma d by 2. And then for derivative dEy over dx, so I will get minus a kappa sine kappa d by 2 is equal to minus gamma c e to the power minus gamma d by 2. If I divide this by this, I get kappa tan kappa d by 2 is equal to gamma, and remember that these kappa have dimensions of 1 over meter. So, I can make them dimensionless. So, I can multiply both sides by d by 2 and get an equation like this, which is kappa d by 2 tan kappa d by 2 is equal to gamma d by 2. What is kappa and what is gamma? So, you remember that kappa square is equal to k naught square n1 square minus beta square, and gamma square is beta square minus k naught square n2 square. K naught is equal to 2 pi over lambda naught. So, for a given waveguide and wavelength, the only unknown in these kappa and gamma is beta. So, this is nothing but a transcendental equation in beta. So, beta satisfy this equation. So, there are only certain values of beta which are possible, and those values of beta satisfy this equation. Only those values of beta are possible. Okay. So, this makes the modes discrete. So, from here I find out what are the possible values of beta, and for those beta I can find out the fields. So, that is how I can get the modes of symmetric planar waveguides, and these are symmetric modes. In the next lecture, I will continue with this to find the solutions for anti-symmetric modes. Thank you.